Morning.
Morning.
I was just given this by Tom that there's a Maria Mayer Award. Her full name was Maria Geppert Mayer. It's given to recognize and enhance outstanding achievement by a woman physicist in the early years of her career. That's kind of interesting. It's a small award of $3,000, and plus a travel allowance to provide opportunities. Very interesting. So, if you'd like to look at it, it's here.
When did she get the award? When did they give it
No,
to
it's
her?
given in her name.
Oh, just her name?
Yeah.
Yeah.
She won a Nobel Prize. She
Yeah.
won a Nobel Prize. And we'll talk about that. But the interesting thing that, as I thought about everything I've looked at about her over the past week, is that there's a struggle going on inside the nucleus of many atoms. And the struggle is that the forces are not, in some cases, perfectly balanced. And so, in order to try to reach a stable condition inside the nucleus has to either gain a proton or lose a neutron, or gain a neutron, lose a proton. Something has to change in the ratio of neutrons to protons inside the nucleus. And this was the real contribution that Maria Mayer made, along with a couple of other people who shared the Nobel Prize with her. And so we'll be talking a lot about this balance of the ratio of neutrons to protons inside the atomic nucleus. And it's interesting to note, as I indicated in the outline, that there is a valley, a line of stability that you can draw, and there are certain magic numbers, just like there are certain numbers that when we talk about chemical stability, when the shells fill, when the outer shell fills, these chemicals, these elements do not chemically combine readily. So there are numbers called magic numbers for the nucleus that indicate stability for those elements in terms of the shedding or gaining of neutrons and protons, which in fact is called radioactivity, right? This is how they either gain or lose. So there are certain numbers of nucleons, nuclear particles, neutrons or protons, that will give for certain ratios for these numbers that will give stability to these elements. Something that was never talked about when I studied physics. She was born in 1906, died in 1972, a relatively young age. Some references say that she was Polish-born, some say that she was German-born. So the town in which she was born, Katowice, is in an area that was sometimes German and sometimes Polish. So the researchers can't make up their mind whether she was Polish or German when she was born, but so you'll find some references say Polish-born, some say German-born. And she was the second woman after Marie Curie to win a Nobel Prize in physics. Marie Curie's daughter won a Nobel Prize, but it wasn't in physics, it was in chemistry. So that, I puzzled about that for a moment, and then I realized what was going on there. Yeah, so she was born in Katowice, or how am I pronouncing that right, Stuart? You don't know. Katowice, something. At the age of 17, she started college. And at the age of 24, she got her doctorate. It was pretty good, huh? And when they moved to Baltimore, her husband got a job at Johns Hopkins. At that time, Hopkins would not allow wives of faculty members to teach. So she worked as a volunteer, just for the fun of doing physics. In 1941, she eventually got a job and worked with Harold Urey, who's a Nobel laureate in chemistry, at this laboratory. In 1946, they went to Chicago, and of course, Fermi was still there, working in his laboratory there, and she got promoted to a full professorship in the physics department, and also worked at the Argonne National Laboratory, but had very little knowledge at that time of nuclear physics. So in effect, she had to learn everything about nuclear physics that she could, and eventually got her Nobel Prize in nuclear physics. She met Teller and Fermi at that time and worked with them. As it says, it's interesting to say, in particular, Fermi was always patient and helpful. They can't say that about Teller. He was abrasive, as I think I indicated last time. Yeah. In 1948, she started to work on magic numbers, and it took her about a year to find their explanation, and several years more to work out the consequences. These other people, Haxel, Jensen, and Suess, gave the same explanation at the same time, and they shared, two of them anyway, shared the Nobel Prize with her. I know Jensen did. I'm not sure whether it was Haxel or Suess. So in nuclear physics, a magic number is a number of nucleons, either protons or neutrons, such that they are arranged into complete shells within the atomic nucleus. The 7 most widely recognized magic numbers as of 2007 are 2, 8, 20, 28, 50, 82, and 126, corresponding to elements helium, oxygen, calcium, nickel, tin, lead, and the hypothetical and as yet undiscovered unbihexium. I'm going to give you some names of some elements I'm sure you've never heard of before. Atomic nuclei consisting of such a magic number of nucleons have a higher average binding energy per nucleon than one would expect based upon predictions. So they're more stable and do not exhibit nuclear decay, radiation, radioactivity, whatever you want to call it. And we'll go into this in much more detail as the lecture progresses. In 1950, Gebhard-Meyer developed a mathematical model for the structure of nuclear shells, published in 1950. In 1954, peer examiners included Max Born, James Frank, and some guy named Windhouse. In 1960, she got a full professorship at the University of California in San Diego. And then in 1963, with her mathematical model for the structure of nuclear shells. She got the Nobel Prize in Physics. Oh, there it is, Jensen, oh, and Wigner. Okay, so she shared it with Jensen and Wigner. So with Jensen, I'm sure it was for the same work. Wigner, I think, was for a different reason. She died in '72 in San Diego, had a heart attack. So we're going to talk first about chemical stability a little bit, just to make sure you understand what is meant by shells, and talk about the inert elements, which are elements where the outer shell, the valence shell, is filled. And then we'll talk about atomic stability, which is nuclear stability, and the ratio of the number of neutrons to the number of protons. The Z number, the atomic number that each element has, is an indication both of the number of protons and the number of electrons in an atom of that element. And of course, the number of protons and electrons are the same for complete atoms, okay? For non-ion atoms, uncharged, neutrally charged, I should say. And then we'll talk about the magic numbers and look at the binding energies of some of these elements and why, or what they are and why they are considered magic numbers, why these elements are not radioactive. In everyday language, a chemical substance is said to be stable if it doesn't react very readily with other elements. Okay? So, in particular, if it retains useful properties in the presence of air, moisture, or heat, so it doesn't corrode, it doesn't decompose, it doesn't polymerize, burn, or explode under conditions of anticipated use, normal environmental conditions. Polymerize, I looked into that a little bit. What happens is that the atom or molecule or compound will form chains of polymers from what is called a monomer, a single unit, and some of the more useful compounds of polymers are this wrapping material, polyethylene, and of course PVC, which is used in pipes. So you're all probably familiar with that material, that kind of material. The magic numbers for chemical stability depends on complete valence shells. So the rule is that a subshell is particularly stable if it is half full or full, and given two configurations, the atom would choose the more stable one. So for example, in copper, copper is just one electron away from stability in its valence shell. So what happens is that an electron from an inner shell jumps to an outer shell, okay, and completes it so that copper is stable. And the innermost shell that it comes from is then half full, so it's also stable. So copper is stable, and you can see here in this animated slide that one of the electrons here is jumping to the other shell and making it complete, stabilizing the element. Later on in the lecture, I'll talk about when certain elements were discovered. And it's interesting to note at this time that copper was the earliest element ever found. And I mean, we're talking about 6,000 years before the Common Era. They knew about copper.
Yeah, this jumping between the S shell and the D shell, that takes place within the atom itself. Okay. So
Absolutely.
it's constantly jumping back and forth within the copper atom.
I can't answer that. I don't know, but I know that it takes that electron goes to the 3D shell.
Okay.
I'm not sure if it jumps back and forth constantly, or if it just remains in the D shell. Anybody know? Yeah.
I don't know the answer to that question, but the inner shells would be complete, like the
Yeah.
one is 1 and 2, the inner shells,
Yeah.
each of those would be complete,
Yeah.
so that would be stable. So the only issue would be the 2 outer shells.
Yeah, the 2 outer shells. Yeah. Yeah, that's why I didn't list the other shells. Yeah. Yeah.
Never do.
Mhm.
That's David.
Okay, so valence electrons are the outermost shell. The outermost shell is called the valence shell. And these are the numbers of electrons that fill the shells. So the first shell is filled with 2, the second with 8, the third with 8, the fourth with 18, the fifth with 18, and the sixth and seventh with 32. So you can see where the number 10 comes from in the D shell. It's a combination of the 8 and the 2.
The electron shell numbers on the left are the principal quantum numbers. You know, for each quantum number, 1 you can have from minus L, minus n minus 1 up to plus n minus 1. So for the first shell, n minus 1 is 0, and then you could have, there can be 2 electrons, and the second quantum number, you have an S shell with your 2 electrons, the same as in the n equals 1, and then you have another, the P shell, which would have 6, and it's the same thing with the 2 and 3. And how they get to 18, you add up all.
Right,
the
right. You
subshells.
just add them all up, right. And you can see there's overlap. In other words, if we look at this, the 3D shell is actually above the 4S. So the numbers overlap in some cases. So the 3D shell is more energetic than the 4S. But the electrons orbit the nucleus in these shells. The first 3 shells hold 2, 8, and 18 electrons respectively. So the first shell is 2. It's complete with 2. The second shell has 2 subshells. I think this is what Jonathan's trying to say. And the 2 subshells hold 2 and 6 for a total of 8. The third shell, okay, holds 18. So it holds 2, 8, and 8. So you add up the numbers and you get the total number of electrons in each shell with all the subshells added up. The outermost shell, again, is the valence shell, and atoms are the most stable when the valence shell is filled with the total number of electrons that it can hold. So here are all the electron configurations, and we'll just look at a couple of them. Hydrogen, of course, the atomic number of hydrogen is 1. Okay? Hydrogen, as you know, has 1 proton in the nucleus and 1 electron in the shell that's going around it. It's not a complete shell, obviously, because it takes 2 electrons to complete that shell. Okay? So hydrogen is volatile. I mean, it combines readily with other atoms. Okay? Most notably, of course, it combines with another hydrogen atom that gives it 2, right? And then that combines with oxygen, okay, to give oxygen, which has 6 in its valence, to give it 8. And of course, that gives us water, the stuff of all life. Helium, on the other hand, helium has an atomic number of 2. It has 2 protons, 2 electrons. And since there's only one shell, that shell is filled. And helium is what we call an inert gas, something which the designers and operators of the Hindenburg would have been wise to not ignore. I don't know if they ignored it, but they used hydrogen instead of helium to fill the balloon.
Because the Americans wouldn't sell them helium.
I'm sorry?
The Americans wouldn't sell the Nazis helium.
Oh, really?
The Americans were the supplier of helium at the time.
Uh-huh. Very interesting. So when the chain, I think, dropped or whatever, dropped to tie down the Hindenburg, there was a spark because it had collected static electricity on its flight, and that spark ignited the hydrogen violently. So hydrogen is not inert, but helium is, because helium has a complete valence shell, as do many of the other gases like neon. Neon, which has an atomic number of 10. So there's your 2 and your 8. Okay? You got it? 2 in the innermost shell, 8 in the valence shell. The valence shell is complete. Neon is an inert gas. So it's safe to use it in fluorescent tubes and lighting because any sparks will not ignite it. It doesn't readily combine. Going down the list again, we come to argon. Argon at 18. So there's your 2, 8, and 8. Okay? So argon does not readily combine and is also an inert gas. What would be the next one? Is there a next one on here?
There's always a next one.
Maybe not.
Krypton, and I think it's beyond the list.
Krypton's be on the list, but that's the next one. Okay. All right. So do you get the idea? When that outer shell is complete, it's inert. I have a
Argon is up there, right? Argon is up.
yeah, I mentioned argon. Yeah,
That's right there.
yeah, it's 18 right here.
Oh, we should be able to figure it out. I think it might be atomic number 50.
I'm sorry.
Atomic number 50 might be the next inert.
So if as 18 and it would be so it's 2, 8, 8, 18, 18.
It's twice the squares.
Yeah, yeah.
Twice 1 squared is 2, twice 2 squared.
I have a periodic chart we'll take a look at in a minute. Yeah. So when we look at sodium chloride, now sodium chloride, as you know, is salt, table salt. The sodium has 1 electron in its outermost shell. Okay? And chlorine has 7 electrons in its outermost shell. So the sodium combines very readily with the chlorine to complete that outermost shell, giving it 8. Okay? So that's basically the idea behind chemical stability. Okay? So everybody understand this idea of shells? Any questions on that? Okay, so now we come to the nucleus. So atomic or nuclear, excuse me, stability depends on the ratio of neutrons to protons and on the number of neutrons and protons in the nucleus. There's a lot of things going on here, okay? As we mentioned before, there are 4 forces in nature that could have an effect on what's going on in the nucleus. Turns out that 2 of them predominate. A third one has some impact, but the force of gravity is basically can be pretty much ignored. Okay? So we're going to be talking about the strong nuclear force, okay? The electromagnetic force, and basically that's the force that repels protons from each other because they are all equally charged, or charged, I should say, in the same way. Like charges repel. So the protons are constantly trying to get as far apart as they can. And the weak nuclear force has some effect, although it's not nearly as strong as the other 2 forces. If there are too many neutrons for the number of protons in the nucleus, a neutron can be converted to a proton and an electron. So if the neutron becomes a proton, the electron is ejected. And an electron that is ejected from a nucleus is what we call beta radiation. Remember, there are 3 kinds of radiation: alpha, beta, and gamma. Alpha radiation is 2 protons and 2 neutrons. Okay? So if you eject alpha radiation, it doesn't necessarily change the ratio of neutrons to protons very much. Okay? So alpha radiation, when it's ejected, is not ejected with anywhere near the energy that an electron, beta radiation, would have. And likewise, beta radiation generally does not have as much energy behind it as gamma. So alpha radiation is basically stopped by human skin, cannot penetrate the skin. But beta radiation can, and of course gamma can. The problem with alpha radiation is that if it's somehow irradiated on food, or if it's in the material that you ingest, or even in the air, if it gets inside the body, okay, it is what we call highly ionizing. It's highly ionizing compared to beta, for example. Why is that? Well, there are 2 protons in alpha, and in beta, there's only 1 electron. So alpha radiation has twice the charge of beta. So it can destroy cell walls more quickly and more effectively than beta radiation. Okay. On the other hand, beta radiation can penetrate human skin. So beta radiation is more dangerous in that sense than alpha. Gamma radiation can penetrate just about anything, depending on the energy level. So if there are too many neutrons for the number of protons in the nucleus, these neutrons can be converted. In other words, the nucleus somehow is seeking to become stable. It wants to get rid of or gain neutrons so that the ratio of neutrons to protons is such that the nucleus, the atom, is stable. Okay? It's seeking stability. And that is the cause of radioactivity. If there are too many protons for the number of neutrons, question.
Yes, suppose I am itching. So do you think it is beta radiation that it is
No,
affecting my...
no, you won't feel it.
Huh?
No, you don't feel. What you would feel from radiation, if it was intense, is a burning sensation, not an itch. Yeah, it would burn you. Yeah, but itching is chemical, I guess. It's not nuclear. If there are too many protons for the number of neutrons, a proton can capture an electron from an inner shell. Okay? So it actually drags an electron into the nucleus. And the combination of a proton with an electron can thereby convert into a neutron. A positron can be emitted. A positron is a positive electron. In some cases, an alpha particle is emitted. And the resultant product, because the alpha particle or the positron may not cause enough of a change in the ratio of neutrons to protons, the product may still be unstable. So many radioactive elements, when they decay, simply become other elements that are still radioactive. Okay? And there's a whole chain sometimes until you finally reach a stable element. Uranium, I think, eventually, of course, becomes lead. Okay? So you don't necessarily get a stable element immediately. You may have to go through a chain of radioactive emissions until you finally reach a stable element. So here's an example where carbon-10 emits a positron and becomes boron-10. Okay? To reduce the number of protons. So here a proton is converted into a neutron and a positron. In alpha emission, uranium-238 becomes thorium-234 plus the nucleus of a helium atom, or an alpha particle. Of course, it says numbers must balance, so you'll notice that uranium-92 results in thorium-90 plus helium-2. And uranium-238 becomes thorium-234 and helium-4. So all those numbers must balance, more or less. The weights actually don't balance exactly. The atomic numbers do balance. Of the first 82 elements in the periodic table, which I show here, don't try to read it, 80 have isotopes that are considered to be stable. So if we look at number 82, it's way down here. Okay? So all of these in that color generally are considered pretty stable. Technetium, promethium, and all the elements with an atomic number over 82 are unstable and decompose through radioactive decay. So that's where the colors start to change. Okay, so this was 82 right here. Okay? So there was only one element there that was slightly unstable. Can't read what it is, but there it is. Then the reds and oranges and purples come in and become unstable. No undiscovered heavy elements with an atomic number over 110 are expected to be stable. 110 is right here. Okay. Therefore, lead is considered the heaviest stable element. For each of the 80 stable elements, the number of the stable isotopes is given. Tin, for example, has 10 stable isotopes. So tin can have a varying number of neutrons in its nucleus, but they're all stable. So tin is very stable. There are 80 elements with at least one stable isotope, but 114 to 118 atomic number chemical elements are known. All elements to element 98 are found in nature, and the remainder of the discovered elements are artificially produced, with isotopes all known to be highly radioactive with relatively short half-lives.
I tell you what to stop calling, right?
Okay. So, how do we produce elements artificially? Generally, it requires an accelerator, okay? And what we do is we bombard certain elements with very high-speed particles and surround the resulting collision area with a magnetic field so that we can observe how the magnetic field affects the curvature of the resultant products. And by measuring very carefully how that curvature is affected, we can determine the mass of the resultant product. And once you know the mass, then you know the atomic mass, so you know how much it weighs. Then you can say, well, I found a new element, or I didn't. So that's how, for instance, Glenn Seaborg found 10 elements. And by the way, he was one of the first people to have an element named after him while he was still alive. Most of the naming of elements after people came after they had passed away. So let's talk about the nuclear forces. I mentioned these before. If we say that the strong nuclear force has a strength of 1, okay? The electromagnetic force, if we say that the strong nuclear force has a strength of 1, okay? The electromagnetic force is roughly 1/137th as strong. So it's on the order of 100 times weaker than the strong force in the nucleus. The weak nuclear force is a whole lot weaker than that. So 10 to the minus 12 would be a trillionth, right? Yeah. So it's a tenth of a trillionth as strong as the strong nuclear force. Very, very weak. And the gravitational force can virtually be ignored because it is a 1 preceded by 40 zeros as strong as the strong nuclear force. However, the other thing that comes into this is that the rate at which these forces change is different. In fact, the strong nuclear force, for the most part, is attractive. It's holding the nucleus together against the repulsive nature of the electromagnetic force. So these two forces are battling unless the two objects involved in the strong nuclear force get too close together. Then the strong nuclear force becomes repulsive as well. It changes its character. And beyond a certain distance, the strong nuclear force drops off rapidly. It builds up and then drops off. Whereas the electromagnetic force has a smoother change over distance.
Does this have to do with the nuclear spin, the spin of these particles within?
Probably something to do with the spin, yeah. But we're not going to get into that too much, yeah. Okay? Okay? So these four forces are at work, and I've drawn this little graph for the two strongest forces. Okay? So you can see the strong force, the nuclear force, is very attractive between nucleons if they're at distances of about 10 to the minus 15 meters, which is called a femtometer. Okay? So from about 0.7 to about 2.5 femtometers, the strong force increases. And then it drops off rapidly. Below distances or within distances of 0.7 femtometers, the strong force becomes repulsive and gains strength. So going down here is a stronger repulsive force. The electromagnetic force is strongly repulsive and gradually loses that repulsive strength until infinity. So there is an area here where both of those forces are repulsive. They're trying to tear the nucleus apart. But then there is an area where they tend to balance. Okay? And if they balance, then you have a stable, pretty stable nucleus. But then there is an area where the strong force begins to lose strength, and the repulsive force still has some strength. So again, it would try to tear the nucleus apart. Does that make sense?
Yeah.
So there's a constant struggle in the nucleus to balance these forces, to reach an area of stability. And it has something to do with how compressed the nucleus becomes, which is determined in part by the number of neutrons and protons. So very heavy nuclei become very dense. And so you can't pack them together too closely. That's why very heavy elements tend to be unstable. They can't get close enough together. So the repulsive electromagnetic force kind of takes over. Okay? And again, at the other end of the spectrum, if the density is very low, okay, then the repulsive forces can again take over. As more neutrons enter the nucleus, the density of the nucleus increases, okay? Density being a measure of how much mass you can pack into a given volume, okay? Something that's very dense has a lot of mass in a small volume, okay? And the separation of the protons in that nucleus increases. As the separation increases, the strong force of attraction and the electromagnetic force of repulsion both decrease beyond 2.5 femtometers, but at different rates. So it's very complicated. But this struggle is going on to try to reach a balance between these forces. Does that make sense? See what's going on? While the most powerful forces at work in the nucleus are the strong nuclear force and the electromagnetic force, the weak nuclear force does have an influence on the conversion of neutrons to protons and protons to neutrons. So the weak force plays a fundamental role in the universe. Without it, for example, the sun would not work because it would be unable to convert hydrogen into deuterium. We also believe that the absence of antimatter in our environment, to whom we owe the existence of the universe, is somewhat due to the weak interaction. We're not going to talk about bosons and Higgs particles at this time. That's for a future lecture. But we will come back to this point a little bit in the next series of lectures. By the way, I'm going to start a series next week on 20th century astronomers, which will eventually lead us to black holes and Hawking, okay? But we're going to go through a lot of astronomers in the 20th century, starting next week. The gravitational force, as I said before, you can pretty much dismiss because it's so weak. The interesting thing about the gravitational force is, of course, that it extends so far. It's got the longest range of any force, but it's a very weak force compared to the others. The strong force, on the other hand, exists primarily within the nucleus. Once you go outside the nucleus, you can forget the strong force. If the forces between the protons and the neutrons in the nucleus are unbalanced, then the atom is unstable. Read that as radioactive. It's got to either get rid of or gain neutrons compared to the number of protons. Stable atoms retain their form indefinitely. Unstable atoms undergo radioactive decay. Most naturally occurring atoms are stable and do not decay. Now, the nucleus of an atom is made up of protons and neutrons. The forces inside the nucleus of a stable atom are balanced because the nucleus contains the proper number of protons and neutrons. These atoms are theoretically resistant to all forms of decay, except proton decay, which is hypothetical and has never been observed anywhere. Unstable atoms are radioactive and decay after a certain amount of time. And we've mentioned before, if the half-life, that is the time it takes for a radioactive atom to reduce the mass of that element to 1/2, okay? If that is a very short period of time, then the atom is said to be highly radioactive. Different unstable atoms decay through different processes, such as the ejection of a proton or a neutron. The conversion of a proton to a neutron, or a neutron to a proton, and the emission of that excess energy in the form of photons, which are packets of energy and light, or all electromagnetic radiation. In many cases, the resulting atom, as I said before, is still unstable. So just because you have a radioactive decay doesn't mean you end up with a stable element. This atom then will decay again to a new atom. And this process continues in a decay chain until a stable form is reached. All this makes sense? Okay, questions?
Yeah. Why haven't we achieved a stability so that atoms do not, so that nuclei don't decay?
Oh, that's a very good question. Well, first of all, some atoms
That kept me up at night, that question.
Some atoms have half-lives that are extremely long. So they stay around for a long, long time. In fact, longer than the age of the universe. Okay? So that's one part. The other part is that these radioactive elements are constantly being reproduced due to certain processes in nature, in stars, for example. Okay? And when a supernova explodes, okay, we can get more radioactive material being spread throughout the universe. Very good question. If the neutron to proton ratio is too great, generally more than 1.5, okay? In other words, if you have more than 1.5 neutrons for every proton, you generally get beta emission. You get an electron coming out. So for iodine 131, it will eject an electron, beta emission, and end up being xenon 131. I think that's xenon.
And it would be ionized? It would be an ion.
No, this is coming out of the nucleus.
Right, but you've now got one more proton than electrons, if it's ejecting the electron.
Yeah, but you gotta,
No, it's charge is neutral. Charge is neutral.
But you've lost an electron.
Well, the electron comes out of the nucleus, not the electron shell.
Electron.
Well, and it's left behind a proton. So you've got an extra positive charge in the nucleus.
Okay, but that electron can be captured. Okay. Yeah.
Okay, but in the process, you temporarily created an ion.
Yeah. Temporarily. Yeah.
Now, does the electron, which shell it goes into, depend on how much energy it has, or, you know, is it
Oh,
going
yeah,
to one
yeah.
shell and kick out the existing one?
Yeah. So there may be a whole chain of events, you know. Yeah. This is interesting, and I'm not sure is scientifically provable, but I wanted to show it to you anyway, as another way of conceptualizing what's going on inside an unstable nucleus. So let's say that a thermal neutron, now what is a thermal neutron? It's a neutron moving at high speed because of tremendous temperature. Okay, we know that the higher the temperature, the faster the particles are moving. Okay, so a thermal neutron is a neutron that's moving very rapidly. Collides with a U-235 atom and creates an atom of U-236. U-236 is unstable and immediately decays into atoms of barium-141 and krypton-92, 3 neutrons, and energy. U-236 has an atomic mass of 236.05. The combined mass of the decay products is only 233.85 atomic mass units. The mass difference is converted to energy according to E equals mc squared. About 200 million electron volts per atom. So, a U-235 nucleus absorbs a neutron. It forms U-236, which has excess energy and goes into violent oscillations, such that a neck between 2 lobes develops. The forces between the protons stretches out this shape, and eventually fission occurs. The nucleus splits. The fragments separate and neutrons are ejected. Okay? So that's kind of a liquid drop model of what can happen in an unstable nucleus. before I go into this, I want to point out this very interesting online encyclopedia. Anybody ever heard of it? Yeah. You can enter any sequence of integers, and it will search the entire range of possibilities and give you a listing of what that sequence might mean.
Searches a range of researches, papers that have produced these sequences.
Yeah. Yeah.
Doesn't search all possible sequences.
Oh, okay. Okay. But there's a lot of them. There's a lot of them. Yeah.
All historical.
Yeah.
You mean a calculated equation relating, you know?
No, it's not, if someone has calculated some sequence and entered the sequence in the database, it will search for it, and find it if you've entered one that's similar to it, or that sequence.
For example,
If you've come across one in your research or something, you could enter it and see what the history of it is.
yeah. For example, if you entered 1, 2, 3, it would come up with Fibonacci. Okay. You know, if you entered enough of them, it would tell you that's the Fibonacci sequence. Okay.
It's not search, it searches research papers that are produced as your sequence. You know.
Yeah.
It searches the research database.
So in nuclear physics,
It's not nuclear physics.
a magic number is the number of nucleons, protons or neutrons separately, such that they are arranged into complete shells within the atomic nucleus. So the idea of complete shells from chemistry, remember, meant stability. So here, the idea means stability of the nucleus. Chemical stability meant it didn't combine readily with other elements. Okay? Nuclear stability means it's not radioactive. Okay? The 7 most widely recognized magic numbers, 2, 8, 20, 28, 50, 82, and 126. For protons, this corresponds to the elements of helium, oxygen, calcium, nickel, tin, lead, and hypothetical undiscovered unbihexium. Atomic nuclei consisting of such a magic number of nucleons have a higher average binding energy per nucleon than one would expect based upon predictions, okay? And I have a graph here that shows what that means. For example, let's look at helium-4. We know that helium-4 has 2 protons, and 2 was a magic number, right? Look where helium is compared to the 2 closest elements. So down here is probably helium-3 or hydrogen. Look at the peak of binding energy. And remember that the higher this is on the graph, the more binding energy it has, the more stable it is. Okay? So there is no reason for helium-4 to decay radioactively because it will be going to areas of lower binding energy. So something that has a great deal of binding to it is not going to be seeking to reduce that binding energy. Okay, it's going to be very stable, very stable. Here's another example. Okay, oxygen with 8 electrons, 8 protons. Okay, so 8 protons being a magic number. And you'll notice that on both sides it would lose binding energy, so it is very stable, not radioactive. Fortunately for us, since we breathe it all the time. The first shell model was proposed by, looks like a Russian, Ivanenko, in 1932. And in 1949, it was developed further by, among others, Maria Mayer. And Wigner, Mayer, and Jensen shared the 63 Nobel Prize for their contributions in this area. The shell model is partly analogous to the atomic shell model, which describes the arrangement of electrons in an atom, in that a filled shell results in greater stability. When adding nucleons, that is protons or neutrons, to a nucleus, excuse me, there are certain points where the binding energy of the next nucleon is significantly less than the last one. So these magic numbers indicate nucleons that are more tightly bound, nuclei that are more tightly bound than the next higher number, and this is the origin of the shell model. Does this make sense? Okay.
Is there a proposed structure showing how the neutrons and protons are arranged geometrically?
Well, we think that the protons get as far apart from each other as they can. So the conception of shells is not really as descriptive as it might otherwise be for a nucleus. And as we found out later, there aren't really shells in the electron area either. They're kind of orbitals with probabilities.
Right.
You know, quantum physics has shown that there really isn't a strict shell.
But they do have a geometric pattern to them, like the lobes of the wave function.
In the nucleus?
No, for the electron.
In the atom, yeah.
I wonder if they had something analogous for the nucleus.
Yeah. There's a better picture so you can see. Oh, okay, so on one side is lithium, and if you go up from oxygen, it goes down in binding energy. Carbon-12 also is a little bit of a peak, but it wasn't considered a magic number. Many of the isotopes of carbon are radioactive, like carbon-14. So the ratio of neutrons to protons is kind of interesting to look at. And we notice that, for example, for hydrogen has no neutrons, so the ratio is 0, normal hydrogen. Deuterium has 1 neutron and 1 proton, so the ratio is 1 to 1. Tritium, and deuterium, by the way, is not radioactive, okay? But tritium, which is radioactive, the ratio is 2 to 1 because there are 2 neutrons and 1 proton in the nucleus. And tritium is highly radioactive. Helium-4 has 2 neutrons and 2 protons, so the ratio is 1 to 1. Uranium-235 is 1.55, 238 is 1.59, plutonium is 1.54, all of them above 1.5. So we think that in the range from 0.5 to 1.5, you get a pretty stable element. But if it goes below or above that, then the nature of forces changes in the nucleus such that it either becomes very repulsive or very attractive, and the nucleus tends to eject and change protons to neutrons or neutrons to protons to reach a more stable configuration.
Did you say before that the magic number 2 corresponded to a stable?
No, very unstable. Tritium. Oh, the magic number 2. Yeah, that's helium, right?
Oh, okay, so this, those numbers are just a ratio of.
Yeah, this is just a ratio, yeah. It's interesting to note, as so many other things in physics and astronomy, there is a line of stability that you can draw if you look at all of the elements. And so I'll read this to you because it's hard to read. This is ZR, what is that, zirconium maybe? Has a ratio of 1.25 to 1. So that would be stable.
That's neutrons to protons.
What's SN? Is that 10?
Yeah.
Yeah, there's 10. A ratio of 1.4 to 1. So it's in the stable region. And up here is mercury with a ratio of 1.5 to 1. So this whole thing is called the belt of stability. Okay? And here's another picture of it. Notice on one side of the belt of stability, you get normal electrons coming out. On the other side, you get positrons. So it's trying either to convert a proton into a neutron or a neutron into a proton in order to reach that line of stability. It's amazing to me that you can draw such graphs, and in a sense, this is the real miracle that is discoverable in science. That you can find these laws that apply across many, many different variables. Okay, I said 0.5, I should have said 1.1. Oh, 1, okay. So if the ratio is less than 1 or greater than 1.5, the nucleus is usually unstable. Okay? Fascinating. For each element with an atomic number Z, that is the number of protons in the nucleus, small enough to occupy only the first 3 nuclear shells, that is up to that of calcium with Z of 20. There exists a stable isotope with an N to Z ratio of 1. So until you get to about 20, let's go back to the graph here, and you can see that up to about 20, the curve almost is exactly over the line, which is a ratio of 1. Then it begins to diverge a little bit. So, with the exception of beryllium, which has an N to Z ratio of 1.25, and every element with an odd atomic number between 9 and 19 inclusive, hydrogen with a ratio of 0, helium 3.5 are the only stable isotopes with a neutron-proton ratio under 1. Uranium-238 and plutonium-244 have the highest ratios of any primordial nuclide at 1.587 and 1.596 respectively. While lead-208 with a ratio of 1.53 or 1.54, it's closer, has the highest ratio of any known stable isotope. So the law is not perfect, but it pretty much applies. 1 to 1.5 is generally going to be stable. Anything less or anything more is generally going to be unstable. Nuclear waste exists mainly because nuclear fuel has a higher stable N to Z ratio than the parts into which it is fissioned. So it hangs around. there are some doubly magic isotopes that have both the same number of, a magic number of protons and neutrons, okay? Among those, helium-4, oxygen-16 with 8 and 8, calcium-40, 20 and 20, calcium-48, 24 and 24. No, that's not right. I'm not sure why that's on there. Nickel, 48, 24 and 24, probably. Anyway, doubly magic effects may allow existence of stable isotopes which otherwise would not have been expected. Calcium-40 with 20 neutrons and 20 protons is the heaviest stable isotope made of the same number of protons and neutrons. Calcium-48 and nickel-48 are doubly magic because calcium-48 has 20 protons and 28 neutrons. Both of those numbers, 20 and 28, are magic numbers. That's the explanation. Nickel-48 has 28 and 20. Calcium-48 is very neutron-rich for such a light element, but like calcium-40, it's made stable by being doubly magic. Interesting.
Huge range.
Okay, I think I've seen that already, yeah. I wanted to bring this chart up. I'm going to read these to you because you can't read them. There are some elements on here that I never heard of. So I wanted to read you some of these names. This is going to be kind of interesting. And most of them are higher weight elements. So we'll start with, let's start with 106. Seabordium, after seaboard. Bohrium, after Niels Bohr. Nassium, I don't know who that's named after. Meitnerium, after Lisa Meitner. Okay? Darmstadtium, after a town, I think in Germany, Darmstadt. I think where a lot of research was done. Röntgenium, after Röntgen, who discovered X-rays. Copernicium, after Copernicus. How he got in there, I don't know. Nenonium, don't know that. Ferrovium, Moscovium, Livermorium, after Livermore, Lawrence Livermore Laboratory. Tennessee, after Tennessee, where it was probably discovered. This is a good one. Oganessium, after Oganos, who was a guy that discovered it. These elements have been undiscovered. So they all begin with the letters UN. So we have unenium, unbinium, unbiunium, unbibium, unvitrium, and so on.
Now, what do you mean by undiscovered?
They haven't been able to create them, but they think they exist. Because the shell, the electron shells could be filled out to that level. Okay? So chemically they could exist.
Yes, if I discover an element, then I can put its name Alium. So my name is Ali and I add U.
Probably, yeah.
That's one
And
under,
all us owls would like that.
that's one under California,
Yeah, it was California, yeah.
discovered in California.
Oh, but that's known, yeah. So here you can see again, and this can be described now. In this color, elements have at least one stable isotope, all of these. So the lighter an element is, the more likely it is to be stable. The green are slightly radioactive, okay? So there's a couple of them up here, but most of them are in the actinide series. Significantly radioactive is yellow. The most stable isotope has a half-life between 800 and 34,000 years. Orange, the most stable isotope as radioactive, has half-life between 1 day and 130 years. So they're pretty highly radioactive. Okay? We got this one, a couple of them, a few of them up here, and this one up here. Highly radioactive, red, the most stable isotope, has a half-life between several minutes and 1 day. They don't hang around very long. They decay very rapidly. And purple, they're extremely radioactive. The most stable isotope has a half-life less than several minutes. Notice they're all the very heavy elements. Okay? So the heavier it is, the more likely it is to be unstable. Yeah. Interesting. Now this chart shows when they were discovered. Okay? So if we look at this color here, it's sort of a light orange. They were discovered, 12 elements were discovered, antiquity to the Middle Ages. Unrecorded discoveries up into the Middle Ages. Okay? So I can name some of them. Iron, copper, zinc, carbon, sulfur, silver, gold, mercury, lead, tin. Okay? So those were known from antiquity into the Middle Ages. The purple, the light purple, from the Middle Ages until about 1799. There are 22 of those elements.
They include uranium too, also. 92.
Uranium,
It's 92 at the bottom.
where is it?
Now over. Where?
They mined that in Czechoslovakia.
In the Middle Ages, yeah.
They mined it,
And they dumped
Yeah.
it
and they
because it
threw
was
it in
useless.
slag heaps.
These were discoveries during the Age of Enlightenment, from the Middle Ages to 1799. So they knew about uranium. Maybe they didn't know it was radioactive.
No.
And a lot of people may have suffered severely because of that.
They collected a lot of uranium from the tailings from old mines because
Yeah.
uranium was thrown out as a useless
Really?
element.
Yeah.
It was a byproduct of something they wanted, like tin or whatever.
Yeah. From 1800 to 1849, the green, the light green. There are 25 elements during the scientific and industrial revolutions. So we have, let's see if I can name some of these. Vanadium, potassium, sodium, lithium, rubidium, osmium. I don't know some of these. Selenium, aluminum, boron, fluorine, bromine, iodine. From 1850 to 1899, the age of classifying elements. This is where spectral analysis techniques came in. There are 24 elements. Okay? So we have, I don't know if I'm going to be able to name any of these. Ytterbium, galenium, germanium. I don't know what those are. That looks like cesium, rubidium.
Samarium, europium,
Yeah.
gadolinium.
Oh, look. Oh, over here. I know these, right? Here are all your inert elements, right? Helium, neon, argon, krypton, xenon, and radon. Radon.
Yeah.
When I had my basement tested for radon, it was kind of high. So what they come in and do is they put a pipe into the sump that I already had dug, and they put an electric pump to pull air out of the sump and pump it up through its own chimney so that I can share my radioactive radon with all of my neighbors.
Your mother told you to share, so you have to share it.
You're a mean neighbor to take them down with,
So, what's the half-life of it?
If you've got a pump, where's the water go?
and they don't even know it.
No, it's pumping air.
Or it's not pump for air?
Yeah,
Good thing
just
we're
pulls
not-
the air out.
So-
And the radon along with it. And the radon level dropped immediately as soon as they
Half-life.
turned it on, yeah.
You let them send to the laboratory, right?
I now live on the 7th floor of the apartment across the street, so when I go out on my balcony, I can breathe in all that.
Chilling up there. Has it gone up that high already?
You'd be extra.
From 1900 to 1949, there were 14 additional elements. The development of the original quantum theory, okay? So that we began to get now into the heavier elements, you see? Along here, along here. So this is where subornium came in. From 1950 to 1999, after the Manhattan Project, they began to have colliders, linear accelerators, so they were able to produce these elements artificially. And so again, you notice these are the heavier elements, okay, all along here and all along here. There's californium, somebody mentioned that. And since the year 2000, recent synthesis has found 5 additional elements. And there's your oganosmium. So we're up to 118. We think we can go to 126. So there are still 8 elements left to be discovered. Now this chart just shows ancient discoveries, and I just wanted to show you this because it's interesting. Copper, 6,000 years, the earliest use was 9,000 years before the Common Era. Amazing. Oldest existing sample, 6,000 years before the Common Era, down in the Middle East. Lead, earliest used 7,000 before the Common Era, and oldest sample 3,800 years before the Common Era. Egypt. Gold, probably used before 6,000 BCE, and oldest sample before 4,000 BCE. Silver, before 5,000 BCE. Iron, before 5,000 BCE. Carbon, 3750 BCE. Tin, 3,500. Sulfur, 2,000. Mercury, 1,500. Zinc, 1,000. Arsenic, 815. Antimony, 815. And bismuth, 1,000. A year, 1,000 Common Era. So those are the ancient discoveries of elements. It's kind of amazing that they were actually able to identify these as elements. I wanted to show you that. In summary then, Maria Meyer led the way to identifying nuclear structure and the importance of the neutron to proton ratio in determining the radioactive nature of certain isotopes. Chemical stability, or reactivity of elements, is due primarily to the status of the valence or outermost electron shell. Filled shells are characteristic of the inert elements like helium and neon, argon. Valence shells with 1 electron combine readily with valence shells that have 7 electrons to completely fill a shell with 8 electrons. So we have hydrochloric acid and sodium chloride table salt, for examples. Neutron to proton ratios that are too low or too high, below 1 or above 1.5, generally result in an isotope that is unstable and emits radiation. Magic numbers of nucleons indicate isotopes unusually stable because they have higher binding energies than isotopes with one more or one less nucleon. Any questions or comments? Yes, sir. Yes, sir.
What is electricity?
Electrons.
Electrons, yeah. Flow of electrons.
Flow.
What is electricity?
Flow of electrons.
Flow, we don't know about flow of electrons. We've never measured a flow of electrons.
Oh, we measured amperes. We measured current.
We measured difference of potential.
Okay.
What is difference of potential? What is the,
Difference of potential is electricity.
what,
You're asking me what is the true nature of electricity?
yes, what do?
That can't be. I don't know that anybody can answer that.
That's why I asked the question.
Well, he was able
It's a good question. Thank you very much. See me after class. Anybody else?
Someone trying to find out.
Yes.
Have up the periodic table, the elements. You know, you have these two rows on the bottom, they're sort of like separated from the rest of the table.
Yeah, the shells don't fill in the order that you might expect.
Okay.
That's why they were set up there. Seaborg had a lot to do with those. The actinides and lanthanides. Thank you very much. Have a great week. Next week, I'll be talking about Carl Sagan and astronomy.